reliability versus life. Full distribution. Okay, so what is variable distribution? Well, when you model some phenomenon and that phenomenon is probabilistic, what you do is you essentially run the experiment and you collect data, and then you see what sort of distribution follows. So for example, many things in the world, like for example, shaft diameters or most production of machine elements follows a normal distribution, which means that, let's say that if you randomly pick a diameter in a sample of 1,000 and the nominal diameter is supposed to be 1.5, then you will see that most of the diameters are in the range 1.5. In fact, you will see that 95% of the diameters are in between what they call plus or minus 3 sigma where sigma is the deviation. And so you have this thing called normal distribution, which explains most of these things. In the case of failure of ball bearings, when people did these experiments, they found that failures follow what is known as a variable distribution. And what this figure shows is pretty much that. That is, when you study the failure and you make a plot based on experimental data, you'll see that there is a peak like this. This is basically where most of the bearing, a big percentage, in this case, 1/4 or 25% of the bearings will have something which corresponds to about 1/3 of the life of the bearing. So you can see on the x-axis there's 1 through 12, and this is in some units, but 1/3 of that basically peaks at some point, which is not exactly in the mean, which at the middle, or at 6. Okay, so that's the variable distribution for you. And you can fit a curve, and the dashed line is a curve which explains, which is basically the variable distribution. So this plot here is known as a PDF, or a probability density function, f of x. So maybe just make a note here. It's empirically found that probability of failure of ball bearings or bearings in general follows a variable distribution. F of x here, as I said, is the probability density function. Okay, so the rule is that if you integrate the area under the probability density function from minus infinity to plus infinity, you should get equals to 1, which means that the probability can only take a maximum value of 1 and not bigger than that. So in this case, since we're interested in the L10 life, we are pretty much looking at 10%. So you can see on the y-axis is the failure. So 10% failure is our cutoff. So you just extend this, see where it intersects the variable distribution, drop a vertical, and then the area here all the way beneath the curve and to the right of the red line is 90% of the complete area. It's the 90% reliability for you. So L10, this is the L10 coordinate, because L is life. So L10 is the coordinate on the x-axis such that 90% area is yellow, the one which I've just shaded. Okay, so why do we need this? Well, I'll come to that in just a bit, but let me just write a formula which relates the reliability, in this case, the area under the curve, with the life, or in this case, I'll parameterize the x-axis with the variable x. And once we have that, I will show you why we actually need it in this case of predicting bearing life. So the formula which gives me the reliability as a function of x, where x is the life, is given by this x minus x0 theta minus x0 raised to b. You note that it's an exponential, e raised to, this whole thing in the bracket, in the square bracket, it has to be raised to e. So x is the non-dimensional life. In other words, it is L divided by L10. So you normalize against the L10 life. X0 is the minimum value of x. So this will be given to you. The moment you have a Weibull distribution, you will be given x0. Theta is the characteristic parameter. It's also a constant, just like x0. It is 63.21 percentile for roller bearing. And B is the shape parameter, which is 1.5 for roller bearing. Okay, so basically you are given the values for these constants. Basically, the value for these parameters depends on the shape of the Weibull distribution. And there are many types of Weibull distributions. You can read about it in Wikipedia. Okay, so why are we doing Weibull distribution? What the Weibull distribution helps us do is we have so far computed the bearing life at 90% reliability, but what if we want to find the bearing life at 95% reliability or 99% reliability? This is where the Weibull distribution will help us. So the next section actually will show you how to go from 90% to different 95 or 99% reliability, which is more relevant in some applications, right? 90% reliability is a relatively low reliability these days. So relating load, life, and the life, load, life, and reliability. Okay, so what we've done so far. So far, we have at 90% reliability, we have FD, LD, 1 raised to a equals FR LR 1 raised to a, where FR we also wrote that as F10 L10 1 over a. So R is the rated where rated is also the R10, L10, or the F10. So it's really it's synonymous. So this is something which is available in catalog. Given in the catalog as a spec. So this is the number which you'd use in order to choose the bearing. Okay, now, as I said, the problem we are dealing with is 90% reliability is not that great. What if you want to find the rated load or the life at 99% reliability, 95% reliability? So how do we compute FDLT at 95% or 99% reliability? Okay, so that's the question we'll be dealing with in this section. Here, what we essentially do is we use these equations which I wrote down and something about the Weibull distribution to make that to compute those things. Okay, so before that, let me draw that curve. This is a curve I had shown. See, where is that? Yeah, here, right here. So a curve of log F versus log L is a straight line, as you can see, and that is at 90% reliability. So let me just draw that curve first. Log N, and then this is our 90% reliability line. Okay, so what happens is if you want to do the same experiment to find the reliability at 95% or 99%, it so happens that you will end up with lines which are parallel to this line, something like this. So this is for a constant reliability, but the reliability is increasing from 90%. Okay, this is line of constant reliability. And then if you do the same experiments at lower reliability, then you end up with lines like this are decreasing from 90%. Okay, so what do you expect is if you do this at different reliabilities, then you'll get lines which are essentially parallel. And so you could potentially do that and get this curve, but that will take a lot of experiments. So what we do is instead of using more experimental data, what I'm going to show you is how to use that Weibull distribution to go from one of these lines, say this one, which is the load line at a catalog rating, to this line or this line. So it will give you basically the load line for a different reliability. That's what we're after. Okay, so we will use Weibull distribution. And load line to compute C10 at a different reliability. Okay, so let's see how to do that. Okay, so I'm just going to draw Okay, so let's see what we have here is the log x, which is log L divided by L10 plot. So it's non-dimensionalized. And then we have log f, the load. And let's say that the line I've drawn here on the right side is the 90% reliability line. And this is an unknown reliability, or either unknown or you're maybe given the reliability, but it's going to be an offset from that catalog line. This is the catalog by a fixed distance. Okay, so here's what's going on. Let's say that we are interested in a design where we want to compute either the FD desired. So we're given FD and we are told to compute XD at a reliability RD not equal to 90%. We write that down. Problem is compute FD or XD at R equals RD not equal to 90%. Okay, so it could be 95, 99, whatever. However, we do have the catalog rating because we have the manuals for the bearings, and that line is the other black line at 90%. So we know. So let's say that one point on this line is, draw that in blue, is this point, and that is something which we know the value of because this is a catalog line. So let's call that X10 because we know the value from the catalog, and then this is going to be the either it's a C10 or, so let's just call that C10. Now, when you draw this line, when you see the dashed line I drew, that line intersects the horizontal line at A, intersects the line at R equals RD at some point. So let's call that point the point B. And we can see that the C10 is same as FB because it's a horizontal line and the force or the load is going to be the same. Okay, so what we are doing now is we know C10, we know X10. We now use the Weibull distribution in order to find what this point is, B is. Okay, so that was the equation I wrote down. And then once we know we are on B, the line which passes through B and D follows the same equation, that is F times L is a constant. So let me write that down here. So the equation is F times L raised to 1 over A is constant is true for this line. It's the same true for this line, but since we are interested in relating B to D, I'm just writing it down for that one. So I'm just going to write down what I said. The solution is step 1, use Weibull to relate A and B along same load FP, which is equal to C10. And once you do that, use F times L raised to 1 over A equals constant to relate P and T. Okay, and that's, once we do the steps, we can actually compute the life or the load at R equals RD. So let's do that. Okay, so first for line BD, I actually do step 2 for step 1 later. So step 2 for line BD. Okay, so if you remember, recollect, BD is this line at reliability R equals RD. We know that FL raised to 1 over A is a constant. So we can write FB equals FD XT divided by X 1 over A. Call that equation 1. That was easy. And now what we'll do is at B and A, we can relate A and B using the reliability equation, which I wrote down earlier. So for B and A, constant FB, we have RB equals exponential XB minus XO divided by theta minus X O raised to minus. Let me check if I got this right here. Yeah, so same equation here. Okay, so let's now solve. So this is a reliability equation, but let's solve for XB and note that RB equals RD. That is, in other words, the reliability at B is the same as the reliability at D because this is the constant reliability line. So we just put RB equals RD and get XB equals X0 plus theta minus X0 1 divided by RD over B. This is our equation 2. We circle the two important equations. This is one of them. And this is the second one. Now, if you want, you can also combine both this equation. Combining 1 and 2. So this is just doing it in one step. We can write the C10 life at a different reliability, R equals RD. Okay, what is that? It's basically the reliability at, in this case, F. So it's at FB. FB equals FD times XT X0 plus theta minus X0 natural log 1 divided by R T 1 over B times 1 divided 1 over A. Okay, so you can use this equation to find the C10 life at a reliability which is different from 90 degrees. Okay, so let's see how to apply this in a formula, in a problem. Okay, the design load on a ball bearing is 413 lbf. The speed of the shaft is specified as 300 revs per minute. The expected life is 30 kilo hours at a reliability of 0.99. Compute the C10 catalog entry at the base of 10⁶ revolutions of rating life. The variable parameters are given: x0, theta minus x0, and b. Okay, so let's try to sort of parse these values in terms of the variables we've identified before. So the design load on a ball bearing, that is the load which is desired, which we want to design it for. So Ft equals 413 lbf. The speed of the shaft is 300 revolutions per minute. So now, since this is revs per minute, this should be n was 300 revs per minute, and this is desired. So let me just put nd here. The expected life is 300 kilo hours. Okay, so since this is the life is in hours and not revs, this should be the abbreviated L, and this would be LD because that's desired. So 30 kilo is 10⁻³ hours. Okay, the reliability at D is 99%, or just put it as 0.99 in the formula. You have to put a number less than 1. Compute the C10 catalog entry. So we need C10 at R equals 0.99 on the base of 10⁶ revolutions of rating life. Okay, and variable parameters are given. So x0 is 0.02, theta minus x0 is 4.439, b is 1.483. Okay, and then there's one piece which I forgot to add. 10⁶ is the rating life, so it will be that will be LR. R stands for rating life, 10⁶ revs. Okay, so first let's just work it out backwards. Let's write down the formula for C10. So C10 at a different reliability is the formula from which I copied from, which I'm going to copy from right here. This is essentially what I'm going to write. So FD XD x0 plus theta minus x0 natural log 1 divided by R T 1 over B. Then this whole thing is 1 over A. Now this is a ball bearing, so I'll just assume A is 3. Okay, so let's see what's given, what's not. C10 is unknown. XD, x0 is given. Theta minus x0 is given. The reliability at D, this is given 0.99. And so FT is the desired, so it's also given. However, we are not given XD. This is an unknown. So once we find XD, we can sub in the value for XD and compute C10. So how do we compute XD? Well, we're given so we are given, so what's the definition for XD first? XD is LD divided by LR. Okay, it's the normalized value for the life. So we always divide the desired with the rated life. So LD is given, LD is not given, but the abbreviated LD is given. So let's write that, relate them. It's 60 abbreviated LD ND divided by LR. So 60 times LD is 30 times 10 raised to 3 divided by LR 10 raised to 6 and that comes out to be 540. So now let's sub that in the first equation.
Professor, do we have to put the ND value as well, like 300?
Oh, did I miss that? I'm sorry. LD, yeah, I missed it, sorry. 300. Okay, the answer is right. I just copied from the notes. I just forgot to add the 305.40. So let's sub that in. So we get C10 equals 413 540 divided by 0.02 plus 4.439 natural log 1 divided by 0.99 raised to 1 divided by that would be B. B is 1.483 1 over A. So if you do this calculations, sorry, A is 3, you get C10 equals 5580 lbf. Some space for this. Okay, can't move this, quite move it. C10 is 5580 lbf. Okay, so that's